Thanks for inviting.
Yeah, and welcome everyone. So I just do the introduction for Frank, but I don't think he needs introduction because people in the area knows him. So I just go through the biography he provided and then over to Frank to the presentation. So today we have Professor Frank Neumann, is a professor and the leader of the Optimization and Logistic Group at the University of Adelaide, and he has been an honorary professional fellow at University of Melbourne from 2019 to 2023. So his current position is funded by the Australian Research Council, ARC, through a future fellowship and focuses on AI-based optimization methods for problems with stochastic constraints. Frank has been general chair for the GECO that we've been talking about on 2016 and co-organized AECM FOGA, Foundation of Genetic Algorithm, in Adelaide in 2013. He's an associate editor of the journals Evolutionary Computation and also ACM Transaction on evolutionary learning and optimization. In his work, he considers algorithmic approaches, in particular for combinatorial and multi-objective optimization problems, and focuses on theoretical aspects of evolutionary computation as well as high-impact application in the areas of cybersecurity, renewable energy, logistics, and mining. And I assume he will talk about this theoretical part today for us. So over to you, Frank.
Thank you very much, Hadi, for the invitation and for the very nice introduction. So what I want to do today is talk about evolutionary algorithms for computing diverse sets of high-quality solutions. It's something that we worked on for roughly 10 years now. And I just want to highlight some results that we had in recent years and present you essentially different application domains and different approaches. It won't be anything really on theory. It will be more on the application, and it will also be more an overview type of thing. So if you want to know details, then of course, please ask questions after the talk or send me an email, and happy to have a chat about these things further. Okay, so let me see. So it's joint work with a couple of people. So there are even much more than the ones that you currently see on the slides. But these are the people who contributed to the most recent work, and especially the work that is contained within this talk. All right, so just that we are on the same page, here's my basic evolutionary computation introductory slide. So evolutionary algorithms, we often consider them as general purpose algorithms. They follow Darwin's principle, survival of the fittest. And you work with a set of solutions called a population. And then what you have a process where a parent population produces an offspring population by variation operators. So usually mutation and crossover. You get a set of new solutions, the offspring population, and then you have to select from the parents and the children to create a new parent population. And you iterate the process usually until a good solution has been found. And you can apply these things, and we've seen many talks already in the Optima series to a wide range of complex real-world problems. They work well for adaptive problems, dynamic and stochastic problems. And what I want to do today is talk about a different area where you effectively uses population not just to get a single solution, but to get multiple solutions for a given problem. Okay, so if you look into the evolutionary computation literature, then diversity usually plays a crucial role in evolutionary computation, mainly because it prevents premature convergence and it enables successful crossover. And if you look into multi-objective problems, then it allows to compute Pareto optimal solutions for multi-objective problems or approximations of Pareto optimal solutions, where essentially you use the population to get trade-offs according to two or more objectives. So the majority of these approaches consider diversity in the objective space, so according to the function values that you obtain. And there has been a PhD thesis in 2012 and work essentially building up towards that PhD thesis. That was the work of Tamara Ulrich and Lothar Thiele as a supervisor, and they explored structural diversity in evolutionary algorithms. And so they were mainly looking into, well, let's optimize a given problem, but have different solutions that look different in terms of the structure, because then you might present that set of solutions to decision makers, and they might say, well, I prefer that structured solution over the other one, and discuss essentially structural properties that were not in mind when designing the objective functions. And diversity with respect to other properties or features could be useful in various domains. And there's been a lot of work over the last at least 10 years in these different areas. So the goal here is now, when we compute diverse sets of solutions, is to compute a set of solutions that are all good, but differ in terms of interesting properties or features. And think of good designs that vary with respect to important properties here. And the goal is then to maximize diversity for a set of high quality solutions. So the aim is really here to maximize diversity and not just use it as a vehicle to get a single good solution. So this is quite different from the standard use of diversity in evolutionary computation, where usually diversity is used to avoid premature convergence and or enable crossover. Okay. So let me highlight one of the areas. So the first one is the one where we did initially quite a lot of work that is called evolutionary diversity optimization. So what we want to do is we want to compute a set of solutions for a given optimization problem that all have acceptable quality but differ in terms of some structural properties. So the goal here is to maximize diversity. So you have a diversity measure of a set of solutions, and that's in EA, that's population. So you would like to maximize the diversity under the constraint that all individuals in your population meet a certain quality criteria. Here you can think of the cost of each individual in the population is not more than a given value Cmax. Okay. So, and this would then give you a set of solutions that are all good and they somehow have this maximal diversity. So that would enable then decision makers to choose from different alternatives and also provide some valuable information on the solution space and might aid you when the problem slightly changes. All right. So the other area that has been considered and that is very related in terms of computing diverse sets of solutions is quality diversity. So quality diversity approaches usually aim to compute the best possible solution in sections of a given behavioral and or feature space. And this provides a different way of solving a problem compared to classical approaches, and we will see an example soon during this talk. And it gives high quality solutions with respect to different feature combinations. And the use of this quality diversity approach can lead to a better overall performance for a given problem. So where it has been used for the first time was mainly in the areas of robotics and games. And recently there have been some studies for combinatorial optimization problems, and I will point out at least one study during that talk. Okay, so let's look into a comparison. So I just try to illustrate the difference in that. So for evolutionary diversity optimization, what you would have a fixed population size, let's say these number of points. You want to have them all meeting a certain given quality criteria, and then you would like to space them out according to a diversity measure as much as you can. Where for quality diversity, usually what you do is you establish two features for solutions, let's say 1 and 2, and you place a grid around that. And for each cell in the grid, if you produce a solution there, you would keep it, and you would always keep the best solution that you can find for a given cell. So that would mean that you start with essentially just a few solutions at the beginning, and then the population would grow, trying to capture every cell within the grid and obtaining the best possible solution within that grid. Okay, so to summarize, EDO works with a fixed population size and imposes a diversity measure, and it aims to maximize diversity among the set of solutions meeting the quality criteria. And then this QD, in terms of map-elite versions, works with an increasing population size and partitions features the behavioral space into boxes and improves the quality of solution within each box. Okay, so these are essentially two major approaches to get to sets of diverse solutions. And so there are quite a number of application areas. In terms of optimization, you can present a set of these diverse solutions instead of a single one to enable discussions for further refinements and see how good solutions distribute with respect to the different components and features of your problem. And in the area of automated machine learning, you can try to evolve instances that differ with respect to different features and show you difference in performance. And you could construct diverse sets of problem instances for algorithm selection and configuration. Okay, so that is essentially a basic introduction. Let me just illustrate something along a problem that we all know. So this is a traveling salesman problem. Here's a very small TSP instance, and I give you an optimal tour. Now, if I give you different solutions that are just 5% away from the optimum, then that set could look like that. And if you think of now that for an optimal tour, one of the edges might not be longer available or you don't want to use it, then here you would have these two solutions that you could use instead. If these three edges won't be in there, you have two other solutions that you could use instead. And for these four edges, you would have these two solutions that you could use instead of essentially that instance, this solution. Okay. All right. So let me come to. I want to highlight essentially in that talk 3 papers, and as said, I will briefly touch on the results and the approaches, but not go into too much detail. The first one is diversity optimization for the detection and concealment of spatial defined communication networks. And the idea here is really to look into a combinatorial problem and compute diverse sets of solutions that somehow are all of good quality. So the problem is we want to construct a wireless communication network for a given set of entities. And the goal is we would like to enable communication and minimize the area that is covered by the senders, and also avoid adversaries that might be present at that time. And we compute a diverse set of high quality solutions to provide a variety of structural different options to decision makers. And I would like you to take that just as an example problem, and you can think of different problems that perhaps you have worked on. So this problem, how it is defined is, so we have nodes here that should communicate with each other. We establish the network by computing a spanning tree like this on the nodes. And then each node has a communication radius that is equal to the longest edge adjacent to that node, and we draw a circle around that node. And the area is then just essentially the area that you see here that is covered by these circles. Okay. If there's an adversary in that area, like this receiver here, we would like to avoid it. So this solution won't be feasible. So we would like to have one where essentially the receiver is not within a radius. Okay? So the optimization variant of that is to find a spanning forest if the underlying graph won't be connected, because it could be that the receiver is somehow close to one of the nodes, and then that would break connectivity. So find a spanning forest with minimal number of connected components that minimizes the area. Okay, and in the diversity version, we would look at computing a set of high-quality solutions that has the edges of the structure in that distributed as equally as possible. So we would have a diversity measure that says, well, the diversity of the set solutions depend on what is the overlap between the solutions, and we would like to minimize the overlap as much as possible. Okay, so and then our algorithm for this diversity optimization would initialize a population, and we initialize that with spanning forests that are good in terms of quality, and we somehow call the quality good if the area is not much more than the area of a minimum spanning forest that we would compute for this graph, because we saw that essentially a minimum spanning forest is not optimal, but it's quite close to optimal for this problem in many instances. And then we would have that evolutionary process here where we create offspring. We accept only an offspring if it meets the quality criteria that we have. And then when we have to reduce the population from potentially mu plus lambda individuals back to mu, then we always remove the one such that the remaining diversity measure is maximal. And the whole process is then iterated. So I just show you some examples how it would look like at the end. So each row is a specific instance that where we took essentially TSP instances. The red nodes are here the adversaries, and what you see here are these areas that are covered and the structure of the spanning tree or spanning forest that we obtain. So you can see that this spanning tree here looks quite different to this one and this one and this one over here, right? And you can observe other things for the other graphs as well. So that shows you that one application of this EDO approach where the criteria is essentially the areas are discovered that should not become too big, and we would like to have structural different spanning forests as the underlying communication. Okay, so the next problem is that I would like to highlight is more in the area of quality diversity, and we looked into a problem called the traveling thief problem. So the traveling thief problem is a problem that has been introduced by our group here in Adelaide roughly 10 years ago also. It combines the traveling salesman problem and the knapsack problem into a multi-component problem. And so there have been quite a number of heuristics for that problem. So the idea is here you have end cities as in the TSP, and you have distances between them. And then you also have, at each city, you have a set of items that you could pick. So you could get a profit when picking the items as in the knapsack problem. But then when you pick an item, then you occur a weight. And the idea is then that the vehicle that you're traveling with slows down, which means that you get an additional cost. I will show you the objective function in a minute. So here's a picture. It has these nodes here. You have to compute a tour as in the TSP, and you have items available at each city that you could pick up, and then you would get a profit, but you also occur a weight. That means when you picked up an item and you occurred the weight, then you get slower along the remaining edges that you need to travel. Okay, so the thief travels along the chosen route, and weight of already picked items slows down the vehicle. So the objective function here, how it looks like is you're getting the profit of what you collected, and then you travel along the edges. These are the distance terms that you get from the TSP part. And so what you pay is essentially increasing with the weight of the vehicle. So the more you pack into your vehicle, the more you have to pay along for traveling along a certain edge. Okay, so here's the overview. There are the profits. This is the renting rate that essentially says how important that cost is here for traveling. And you have the travel terms to travel from one city to the others, and that gets increased with increasing weight. Okay, so what we do now is we aim to compute diverse set of high quality solutions differing in the TSP and knapsack score. And we also want to use quality diversity to get something somehow better than other approaches have done before. So then for QD, what you do is you establish a behavioral descriptor that depends on the length of your tour and the value of the items that you have collected. So essentially, these are the two objectives that are coming from the TSP and from the knapsack part. And so what is known about the traveling thief problem is that if you just optimize these things separately, the TSP and the knapsack, then usually you don't get an optimal solution. So you can usually improve by that by getting something that is good in terms of the tour value, and that is also good with respect to the profit, but both things don't need to be optimal. Okay, so and what you can do is essentially you can just look into different heuristics that you know for the knapsack and the TSP part. For the TSP part, you can use solvers, and for the knapsack part, you can choose solvers. And this is essentially what we use as part of that. For the TSP, we used EAX or 2opt as the algorithms. For the packing, we use dynamic programming and an EA that is using bit flip mutations. And they would then operate on these different parts, the tour or the knapsack part of the problem. So the interesting part for the quality diversity approach is now to come up with that map. And the first coordinate, as I said, is essentially the TSP part. That would be the TSP score. So where F star would be either the optimal TSP score or a good score that you would obtain by just running a TSP solver on your given instance on the TSP part. And the second feature would be the knapsack part, where G star would be the optimal knapsack value or something that is good. And then have parameters that tell you, alpha 1 is telling how much are you willing to give up in terms of the optimal TSP score? So that would be a parameter. And alpha 2 would say how much do you go down in terms of the best profit score that you see for the knapsack instance. So we set parameters based on initial experimentation. But this would then give you essentially a grid where for a given solution, you would compute the TSP score that would place you in a column, and the resulting knapsack score that would place you in a row. And then if you're ending up in that cell, you would keep in that cell the best solution that you found according to your TTP score. Okay. So and here's the map elites algorithm, and the parameters were essentially 5% and 20%. 5% going up in terms of the TSP tour and 20% going down in terms of knapsack score. So you would fill that grid now with solutions. So if you get a new solution and it's going into a cell here that has not been occupied before, you would just place it there. If a solution using your evolutionary algorithm would go into a cell that is not empty, you would replace the current solution if the new solution is better. And this is essentially what this algorithm is doing. It's just creating a loop now that is creating solutions over and over again, trying to fill out that map. And we can look into some results. So what we can do is, for these different algorithms and algorithm combinations, So for the TSP part here, EAX and the dynamic programming approach on top of that, to get the optimal packing, we would then see the areas that get occupied by the algorithm, and the quality of solutions of the TTP score, essentially, if it gets more red or darker, then the TTP score would be better. And you can see that here for this algorithm combination and instance, here the best solution would sit at that point. For this EAX and EA, the best solution would sit at that point, and here it would sit there. But overall, what you can see is that the best solution that has been found is not sitting furthest to the left and up, which would mean that you would get it by computing just the optimal TSP tour and the optimal packing plan. Okay, and then what we also saw for larger instances, we saw that based on the results that we obtained, that we were able to beat the current best results in that area for quite a number of instances. For the smaller instances, we were quite close to the best results. For the larger instances, we could get better results than that were previously known in the literature. Okay, so let me turn to the last example in terms of diversity optimization, and that is quality diversity for time use optimization to improve health outcomes. That's quite a different application domain, and we work with people from health science on that. So the motivation was that time is usually limited, and how you spend your time during the day has a strong impact on health and well-being. So you have daily activities such as sleeping, sitting, walking, running, and how much you do of them would impact different health outcomes. So the idea was that we wanted to provide a tool to allow people to structure their day to achieve health outcomes that are good for them, and also look into what are the different trade-offs and how different combinations of activities would look like. And what we do was we provide a tool that is mainly currently a web page that shows improvements in health outcomes based on daily activities for children. So everything that I'm talking about now is based on some data sets that have been collected by our colleagues in health science, and they essentially build prediction functions based on activities to health outcomes. So on a technical level, what we are doing, we were looking into using this quality diversity approach to provide a picture on the impact of activities on health outcomes that we would have. Okay, and then we also looked into interactions between different health goals that you might have when allocating time for the different daily activities. Okay, so let's look into a simple setting where you have different activities. So you essentially have 24 hours during the day, and you could spend your time on sleeping, sitting, light physical activities, or moderate to vigorous physical activities. And then the prediction model that we got from our colleagues in health science was essentially taking these activities and building a prediction in terms of body mass index, cognitive behavior, life satisfaction, and predicted maximal aerobic power. Okay, so what we did then was to build essentially a tool where you can set your objective, let's say academic performance here. You can set your constraints in terms of how much you want to sleep, how much you sit, light physical activity, and the remaining constraint would be then on the fourth variable. And then it would give you the optimal objective for your ranges and essentially how much time you should spend on them, but also a picture overall, according to your feasible range, how solutions would look like if I just fill it out according to the different options that I have according to the constraints. So what you can see here is it's looking a bit like the quality diversity approach where you fill out a space partitioned according to the different minutes that you spend on different activities, and then it would highlight in color the score that you would get, the best possible score that you would get for that combination. So feel free to take a look at the web page, and there's a QR code here. Okay. So let me explain a bit what is behind that. So the first behavioral space was on decision variables, and you can do that also on objectives. But let me explain that for the decision variables. So setting up the behavioral space, we partition essentially the whole thing into cells, as we saw already for the TTP. But here we have the number of minutes according to sleep that we spend and light physical activity. If you have then more than 2 decision variables, you would get a higher dimensional grid, but let's explain it here. So you have these 2 variables, you establish the grid as we already had for quality diversity, and we find the best performing solution for each cell, okay? And then at the end, after we computed everything, so the user can set their own boundaries, and this would be the stuff that would be displayed. And if the user set this boundaries, then we would display essentially this part. If the boundaries are set like this, then we would display that part here. And we report the best solution within that area. Okay, so the map elites algorithm, we saw that already before. What we do here is we generate the map by an EA here. There are just some specific operators in terms of mutation and crossover, but I don't go into details of these. So we choose 2 solutions at random and create a new solution by crossover and mutation. If the cell is empty, then we place it there. If we find that the cell is occupied and have a better solution, then we would replace it. So it's the same scheme that we saw before. And in this way, we can essentially fill out these cells. So the first thing that we looked into was this 4-dimensional problem, and you can essentially just enumerate everything with brute force. So we wanted to see how the EA compares and whether we get all the cells. Okay. And we only showed areas where we had reliable data and were able to do the prediction. So this is why you see the areas highlighted here. So there's these different variables along the edges. So sleep, sitting, and light physical activity. And the rigorous activity would essentially take up the remaining time. And then we again highlighted that in terms of color, what would happen for the BMI score. So what we see here is that the figures of this brute force thing, where we just enumerated everything in 1 minute time intervals, looks pretty similar to what we get for the EA. And that was essentially our sanity check for the 4-dimensional thing. Okay. And then we moved on to do this for higher dimensional problems. Especially we wanted to see how that is when we have 7 input variables where we could not do brute force anymore. And we wanted to see how this map elites approach essentially performs for these problems. And let me give you some results and how the setup looked like. We will show just 2-dimensional subspace to get some insights into the results, because otherwise it's really hard to visualize. Okay, so the 7D problem had a bit more fine-grained activities that you could do. So you see these 7 activities that you essentially can do, and that it was a different data set that we had. And then predictions were from these 7 variables into body fat, academic performance, and life satisfaction. And so the first example that we see is essentially how much school time and physical activity was there, and what was the impact of these on life satisfaction. So what we see from these plots and what came from the data, that the data was saying that the lower school time, the higher was the life satisfaction score here in that data, and the best life satisfaction solutions correspond to moderate allocation of physical activities. These are essentially the solutions that are sitting over here. Okay, and then the other thing that we look, just to put it quite the opposite, is to look into this academic score, where we also have physical activity and school time. Then, of course, physical activity, so the school time highly impacts the academic performance, of course, and so the academic performance increases with school time and reduces with the amount of physical activity. Yeah, sorry, that. Okay, and then the other thing that is interesting to look at is to say, well, we look also into the objectives, because what we can do is we can just look at the combination of the decision variables, compute their predicted life satisfaction and the academic performance, which would essentially identify a cell here, and then store in that cell another objective score, here the score for body fat. And so that would not then depend on the decision variables, but show the interactions between essentially different outcomes that you would achieve by spending your time on different activities. And the healthy body fat percentages were here in the green range, and they correspond to good life satisfaction health scores. And the higher ones correspond to lower life satisfaction, at least for the data sets that we had here. All right, so let me conclude. So I wanted to talk about evolutionary diversity optimization and quality diversity. So these are approaches that allow you to compute diverse sets of solutions using evolutionary computation methods. They often provide you with high quality solutions with different structural or behavioral properties. And hopefully we saw that there are quite a different range of applications where you can use them, from communication networks to the traveling thief problem over to an application in health. So the current interest for me is a theoretical understanding and analysis of these approaches. I haven't talked about these things, but there are quite some results. But it's very interesting to establish further advances in this area, I think, and application of these techniques to combinatorial problems and other interesting real-world applications. All right, thank you very much for listening.